Hey guys, so with the holidays coming up and our customers going on vacation, we get to throw all of our engineering time at fun projects now. This Vitpillin we've been working on as a track bike for the spring for me. And one of the big problems is this 5 pounds of unsprung mass sitting on the swing arm. We're going to be taking that and developing a composite part that is hopefully just as strong, but much, much lighter. Okay, yeah, do you want to just start with the license plate?
Yeah, so that's just on these like cursed wing nut spring combo things.
Yeah, I don't really know what the whole deal with this is. Okay, so hopefully when this comes off, that whole bracket is free. Okay.
Oh, there we go.
Well, let's call it 2.5 kilos.
Yep.
So that's what we're trying to beat. All right, so this is the license lace bracket on the Vitpillin we've been 3D printing parts for. First of all, it's 2.5 kilos. It weighs a lot. And we think it weighs so much because it's got to do a whole bunch of different jobs for a whole bunch of different global markets. But all we care about is that it keeps like water off my back and it holds the license plate with a light so I don't get pulled over. The 2.5 kilo weight is actually a lot worse than it sounds because of where it's positioned.
Yeah, so the further you are away from the swing arm pivot, the more the weight impacts suspension performance. At the wheel, it's the weight of the wheel. Out here, it's 2 to 1 compared to the wheel.
Because moment of inertia is proportional to R squared.
Yeah.
So this 2.5 kilos is like adding 5 kilos to your wheel, which is like going from a super lightweight racing slick to like the worst out of balance adventure tire and like an extra like half pound of like wheel weights to get it to not explode. I think we can make something that keeps all the aesthetics of a clean tail up here that weighs at least half as much. And I'm gonna compromise here on aesthetics for performance, but the other thing we're gonna do is make this easy to remove. So when we go to the racetrack, it's like 3 bolts and it just comes off entirely. So similar design, we need a fender, we need a light, we need a license plate. And it's probably going to mount kind of the same to these 3 mounting points that we have for this guy. The scary thing with this is how do we keep it from breaking?
Yeah.
And the first thing we have to understand is like, what are the loads it's under? So the largest load this is exposed to is, you know, if you hit a bump or a curb or a pothole, the wheel gets thrown up at a pretty high acceleration and this has to resist that acceleration.
Yeah.
So that's kind of the magic thing is what is the acceleration that the unsprung rear end of my bike is going to experience? So we've done a little bit of research. So what does Formula SAE say?
Formula SAE says 3 Gs of acceleration, but you have to take the caveat that that's on a clean, prepped racetrack where there's hopefully no big potholes or speed bumps or anything.
Yeah, and then I did the lazy thing and I asked ChatGPT.
Yeah.
And it gave me a range of 3 Gs for racetrack.
Yeah.
It gave me like 3 to 5 for like road. And it gave me a range of 10 to 20 for off-road. I think 25 Gs is like Dakar, which is racing things through the desert at 200 kilometers an hour. So I'm going to say this is probably not enough because we're not on a racetrack. We're not racing Dakar. So I'm gonna say that like somewhere in this range is what we're going for. And I'm pretty content with like 10 Gs as our design target. Like anything much more than that, and like it might crack or break, but
You're also
I'm
getting
more
thrown off
worried
the
about
bike.
myself at that point. Yeah.
Yeah.
The weakest part of the bike is me. I am a bag of meat. And I don't think I can survive much more than that. So we'll go with this as our design assumption. And how much does this whole system weigh? I think we can get it down to like 1 kilo.
Yeah.
At 1 kilogram, at 10 Gs, what's that force we're going to experience?
About 100 newtons.
98 newtons.
Yeah.
Which is equal to also about 10 kilograms, or how many pounds is 10 kilograms?
22 pounds.
22 pounds. Cool. And that feels like a sensible number. If this can support 22 pounds statically, it's probably not going to explode going over a pothole.
Yeah.
So we'll start off by like designing and simulating this.
Yep.
Once we're done with that, we'll probably do some destructive testing and just make sure we can actually dangle a 20-pound weight on the end of this.
Yeah.
Sweet, let's go get to CAD.
Sounds good.
So let's clean stuff up a bit, cover it in 3D scanning spray, and get everything digitized. Oh, weird. This area it's not really doing anything on. My chicken strips, Stanley.
We just highlighted your chicken
We
strips.
highlighted my
Wow,
chicken strips.
that's a hilarious phenomenon.
Can we go heavier on my chicken strips?
Nah, I don't want to waste it. It's kind of expensive.
Oh, I just have to not be a coward?
Remember this shame.
No. So what are you looking for when you set the brightness?
You want, it says right here, adjust until it gets slightly reddish.
Okay.
So see how there's like a hint of red on
Yeah.
the spoke? So that's like, we're on the lower, like we have barely enough. If I bump it, you can see like there's plenty of red.
Yeah.
I wouldn't go more than that. Okay, so this will be a challenging part, is getting it to bridge to the tail. That's why I scanned a bit up here. Basically, when you transition from like large distances, if you get the peripheral, it'll maintain tracking. But this might be tough. It's not really picking up the tire. Yeah, so lost tracking. I'm gonna pause it and then regain tracking.
It doesn't make any garbage data. No.
So when you lose tracking, if you like point really off into the distance, it won't realign, right?
Yeah.
So you'll minimize any risk of regaining alignment briefly and then creating
Ghost.
garbage.
Yeah, okay. So what you talked about was you want to trim some of the stuff I don't need to minimize the size of the mesh.
Yeah.
I think that looks quite good now.
So don't worry, this computer is a little low on RAM. It just warns you,
Okay.
but it'll do it. So we might have to come back in like maybe 15 minutes. That's fine.
Okay. Dude, you scared.
We lost all our work. This page is like, most of the time I just leave it. Because there's another page that has some more optimizations. Okay, so Fusion tends to lag if the STL is too large. I like to keep it under 50 megabytes, and any more is good. So I just simplify the model down. I'm gonna make Bob's life a little better. So I'll make his file like 35 megabytes. And all it does is it reduces the number of triangles in the mesh. So you'll technically lose a little bit of detail, but if the surfaces are mainly flat, that's not an issue, right? We're gonna align the parts. Let's create feature. Okay. So I'm gonna pick 3 edges on, I don't wanna use the tire because it's technically not precise, but what's really precise is the wheel. So put a point here, create, and now I wanna make a line. So for line, I'm gonna pick the middle of this. And the nature of this kind of stuff is you're doing a lot of eyeballing. That's a line straight through there. And then the origin.
Okay. That's pretty separate.
Great. So now we align it. We'll pick our plane, which we made earlier. And here we have like front, right. So I want the front to be when we look at the wheel face on. So I'll make the plane define Y axis negative. And the line I want to be the X axis. And the point is just the point. So now when I click front,
Oh, that's awesome.
it's actually straight. Yeah, so
That is perfect.
that's good. And it's ready to export. So all I do is,
Now that we have our 3D scan complete, we're going to bring it into Fusion where we're going to be doing the rest of our design work. We always found that using the insert mesh tool instead of importing it in the sidebar resulted in getting the orientation and origin aligned more reliably. So I'm going to be doing that here. It should be imported in all the right units by default, so we'll just leave it there. Now that we got our mesh imported, our next step is to add some planes onto our mounting geometry so we can actually start building some parametric models off them. First thing you want to do is go to this direct edit tool in Fusion and select your mesh, and this lets you direct edit the mesh. You can see it's selectable now. And I'm just gonna use the 3-point plane tool to start laying out planes across my mounting geometry so I can draw sketches on them. You'll notice the planes are never perfect because, well, the mesh isn't perfect. But this is kind of exactly what I'm looking for, that it's not obviously tilted forward to back or left to right, and that I've got a roughly equal amount of my mesh below and above my plane. So that one's good. I've got 2 more to draw over here. Same tool again, 3-point mesh. We've got all of our planes on our mesh now. There's just one more plane I'm gonna make, which is this offset plane. This offset plane is offset from the CAD's point of origin and is in line with this top plane here. Instead of designing directly on here, I'm going off this offset plane because I want to keep all my geometry true to the CAD origin. If I don't do that, I'm gonna end up with like a whole bunch of cursed numbers where like vertical isn't 90 degrees, it's like 99.1 or 89.6 or something like a little bit off, and this just simplifies all of that. Doing the CAD for this license plate mount is actually pretty straightforward. There's only one thing that was hard for me, and it's this first sketch which defines all the critical geometry and how it interfaces with the swing arm. There's 2 things here worth talking about. First one is these mounting holes. These mounting holes are exactly 45 millimeters apart. Along that same line, we have this bottom edge of the swing arm mount, which isn't exactly in line with this plane I made earlier, but that's okay. We're just defining it to be 90 because we know on the real part, that's what holds true. The rest of the CAD is actually, it's a little tedious, but really straightforward. I start with like my big blockouts of like my overall shapes. You know, I cut things down to avoid hitting parts I shouldn't hit, and start building the structure out in like simple large blocks. My last pass after that is adding all of my detail and design. So the cutouts and like my chain guard mount. And that's really about it. If you go to the end here, it's just a few more features, adjusting the rotation a bit and adding all my fastener and mounting hardware. From here, before I get out of digital land, I'm gonna go and simulate this based on the load cases we developed downstairs. Now that we're in the simulation workspace, we more or less just work left to right across the top bar and then run our simulation. Materials are important. So we want to set this to our Pantheon materials, which is our CF nylon, which is what we're going to be printing out of. I just made these materials based on our data sheets online. Anyone else can do this for whatever materials you're printing out of. And then the next big one is constraints. So this guy, we do have a bit of work. We have to tell the simulation what part is fixed. In this case, it's really just the bolt locations where we're attaching this to the swing arm. After those constrained faces, we're gonna add some bolt connectors to fix the 2 parts of our fender assembly together. Here we'll specify the type of torque we're applying, which is going to be 10 Newton meters. And then we'll change the material properties of our bolt from our study materials to generic steel should be fine. And we'll do that again for all 4 of them. Now that our constraints are done for loads, we're just going to edit gravity. We talked about 10 to 20 Gs. Gravity is 9.81 multiplied by 15, 15 Gs. Just modifying gravity as a loading constraint, we don't really have to do anything else. It's gonna apply that evenly to the whole part. And we'll hit run. Sweet, so our results completed, and we'll just cover all the things that I always look for. So this kind of results overview, our minimum safety factor is 1.4. which first look is not great. Anything less than 1 means your part will fail. This means we're getting pretty close to the part failing. But simulation results are a bit like reading tea leaves. You can't really take them for face value. You can see that there's a legend below for safety factor, and blue is the maximum safety factor. It means over 8x. And most of this part is blue. Our maximum safety factor is 15, which is arbitrarily high. I think that's actually the highest value this simulation can result in. So what I like doing is just scrolling back on this bar so it starts highlighting only the regions of low safety factor. And you can start seeing where that 1.45 or 1.42 is coming from. And it's coming from this tiny, almost microscopic area above this dovetail cutout. Now, this is probably just my fault for doing bad CAD. There's a seam here, there's a line here, and there really shouldn't be. This probably resulted in a simulated stress concentration, but in reality, there's so much material supporting that point. It doesn't intrude anywhere into the part. I'm calling this like an artifact of the simulation and not something I'm going to experience in real life. At this point, I'm happy to just go and print this part and do some testing both on and off the bike to validate whether my assumptions here were correct. First thing we'll do is we'll split this to objects because it's just one giant assembly right now. And we will make some more build trays. So we have our support arm, the fender itself, and some trim parts. So I'm going to run the trim stuff by itself because they're just fast and low risk. These are the two guys that really take some work to align. Slicing these large structural parts for a 3D print, you really want to be careful of your layer orientations. The parts are just way stronger in the XY plane than across the Z. So you want to make sure that you're putting your load through as much continuous extrusion as you can. And the other thing you want to balance with that is with a part like this, you're definitely going to need supports where your supported surfaces are and minimizing the amount of support pain you have. This is definitely a lot of intuition. So with this part, I know loads are really going like this. Like these two beams, I want as continuous as possible. And this mounting section, I really don't want layer lines going across like this. I don't want this to split. I want my layers to go across this way. And that kind of creates a bit of a conflict here because those are two different orientations. So we're going to play around with the rotation tool and try to find a happy medium. So I think what I want to do is bring this up close to vertical. And then what I think I can do here is if I just lay this whole part over to 45 or even a bit past 45 degrees and then rotate this so it fits on the bed. I think this will be a good compromise because I'm not having like just layer lines going right across the bolt holes. They'll at least be going across diagonally. And then my high stress areas, which right here was what we found based on the simulation, have layers going all the way across. So all the stress we're experiencing is, perpendicular to our stress lines. The top surface here is what you're actually going to be seeing. So that's all going to be unsupported. And we'll need some supports on the bottom, but that's okay. Like no one's going to fucking see them. As far as materials, we're going with PACF. It's our strongest and stiffest one. And then for supports, I'm just going to go to automatic tree supports. And automatic tree supports just kind of work most of the time without you having to mess with them much. So if you take this guy and you go layer by layer, you can see that the layers cover a lot of material. There's no real, there's no really thin points where you're going to be pinching across it and straining the Z bond. And where we really care about it over here, it's got a ton of strength in the orientation that we're printing it. If we go to the other parts, this guy is honestly kind of perfect how it sits. Yeah. We got some ugliness with supports in here, but the fender is going to look beautiful like this. There's no supports on that face. And same thing, our high stress area is going to be very well supported in layers. These guys, we're just going to use the auto orientate function. It kind of figures it out pretty well, especially for these big flat parts. And if we just want to go through each of our trays, we've got this guy, which is 11 hours, and will weigh 260 grams. We've got this guy, which is going to take 9 hours, a bit over, and weigh 250 grams as well. So our total part mass is about, 500, 550, which I'm super stoked about because the original part was, what was it, like 2.4, 2.5 kilos? That's a massive weight reduction. Okay, that looks solid. So we'll just support remove both of these guys. I like these for getting these edge supports. You can kind of just like pinch them and they pop right off. I'm just scraping any kind of remaining support bits. Last things are these flat surfaces for mounting. So they hit and deburr the edge. See the high spots we just took off? And just like a machine part, we're just gonna deburr the inside of these holes a bit. These areas that we sanded, we're just gonna hit with the blowtorch. And then let's take this guy out. Before I go any further, let me just test fit these guys. Oh, that's great. It's really nice having materials that you can just hammer into. Cool, that looks pretty good. And we can just bolt it together now. And then how does this fit into the cable track? It's a little bit tight.
Okay.
So I'm gonna just grab our handy carbide burr tool.
Yeah.
And I'm just gonna open it up a bit. Yeah, I completely overestimated how much squish you needed on that cable for it to be retained properly. I don't know why I wanted to go 10%, but it does not work. Okay, so I think we're ready for assembly now. So that fits through easily now. And then if we rotate this a bit, we know that, so that kind of wants to go right there.
Okay.
I don't think that cable's like ever moving again. We can rotate this retainer here. And let me just give that a tighten. And then that can still slide. Sweet. This stuff has saved my ass so many times. When you don't have waterproof connectors, you can just make it waterproof with this. Okay, that
Right.
just tucks in there.
And contact.
Perfect. Okay, I'd say that's a success. Okay, so we finished the prints last night and they all went together pretty well. But before we're gonna take this out and do some road testing, we just wanna confirm our simulations in the lab. So what we have here is a big bar of metal, which is our swing arm. We've got a random wheel from like a 1978 Trail 90. And we've just bolted this thing together on a pivot on the table. This is like the 80-20 of actually a good setup. These are our print head boards. We've got one mounted on the fender. We got one mounted on the swing arm. The nice thing is they have accelerometers in them. So we're gonna be using those to actually measure the forces that we're experiencing. So back on the board, we were looking at 15 to 20 Gs of load.
Yeah, max
of
load.
impulse.
Yeah.
Yeah. So we're gonna just lift this higher and higher. I've got a little angle guy here so we can see, like, try to be somewhat consistent. And the goal is get to 20 Gs, don't break the bracket. If we can do that, then we can say that our real world testing, at least this version of it, will validate our simulations and I'll be safe on the road. So we have we have two spots we're grabbing accelerometer data from.
Yeah.
We have the swing arm, which we think is, I think this is gonna be a higher impulse here.
I think it's gonna be lower.
Okay.
Because I
well,
think that this guy's gonna whip.
so we're gonna do both.
Yeah.
We're gonna start with the accelerometer mounted on the license plate bracket. And Alex has the data going. I am going to lift it with precision. Okay, so we're starting at -7 degrees. So I'm gonna go up to about 20. Ready? All right, what do we see there?
So we peaked out at about 250 meters per second squared, which would be about 25 Gs.
Really?
Yeah.
From that?
Yeah. Well, think about what the rest of the motorcycle would have to be doing
If
for the
the
back
wheel-
wheel to do that.
Okay, all the way up. F it.
Cool. Let's see what we got. Okay, this time we peaked out at about 277 meters per second squared, so like 28 Gs,
Okay.
27 Gs.
And last time was 25?
Yeah. I think the tire does a lot of work here.
Yeah. You're right. There is some whip there.
Yeah. I think that's mostly what you're seeing is the whip.
Let's move to the swing arm mounted accelerometer.
Okay.
Because I think that all the data we're looking at was like at the axle.
Yeah.
And I think this is our closest approximation to the axle.
Yep, let's do that then.
Okay, this is going to be the swing arm mounted accelerometer, and we'll do 20 degrees all the way up.
Yep.
Okay, 20 degrees.
Cool. 167, so
15,
that's more than that. It's like 17 Gs.
17 Gs. Okay. Let's just go all the way up because we know we can survive it.
Yep.
Okay, so just for context, that's 73 degrees. Our angle boy.
So we peaked out at 185, so 19 Gs?
Okay. So let's do one more where I just throw it as hard as I can.
Yeah.
Cool.
I want to see this thing break, dude.
If this doesn't break, you get to have, oh, we can just print another one.
Yeah.
I forget how nice it is to have digital designs. So like, okay, so this next one, Miles, do you think should I throw it down gently or do I just throw it down
I think
as
you
hard
eat
as,
it, dude.
I just
think
eat it?
you try and get it to bounce
Okay.
all the way back up.
All right. All right, let's see what we got there.
Okay. 111.
But like, okay, at this point, like anecdotally, even before we look at the data,
Like,
I'm not worried about
my,
breaking
my,
this.
my vibes-based engineering assessment is you're fine, bro.
Yeah.
Still peaking out at like 20,
20
22 Gs, 23 Gs.
23? Okay. So tires do a lot.
The tire does a lot. I think if this was like rigidly, like if this was like a metal block, I think you could probably double or triple that number.
You want to take your tire off and risk your rim?
No, it's a nice
Okay.
rim.
I just want to try one last thing because I'm curious at this point.
Yeah.
I'm going to put a 2x4 here.
Yep.
So the swing arm hits a 2x4.
Yeah,
I
do
just
that.
want to see what happens.
Yeah. Let's do that.
Okay, this is our crustiest 2x4 chunk.
There we go. There we go.
And it immediately exploded.
Yeah. All right, let's see what that peaked out at though.
Okay, that broke. Hilarious. So it just shot the top and bottom fender off. You got all of that on tape, right?
Yes.
Okay.
I think it just clipped out our accelerometer.
Okay.
So like it's still reading like 28 Gs.
Okay. And that's why, boys and girls, tires are awesome. I did not expect that much.
It just blew up. Yeah.
Yeah. Well, we did say we were going to test it to failure.
Yeah.
But you know what the nice thing is? It's two parts, so like we don't have to reprint the back of the fender.
Yeah. That's sick.
That's
you.
my motorcycle falling from like 4 feet with no tire.
Yes.
Oh God, I'm just shocked by how much a tire does in terms of suspension.
Oh yeah, totally. It's like
Like I know it was effective, but okay. So I think that's a wrap for our lab testing. Let's go. I'll just go take the bike outside. Well, let's go find all the pavement we can in the neighborhood.
yeah.
I am no longer concerned at all about the safety of this part. Okay, since we already broke this one, the last thing is like, I want to see if I can stand on this and how far up it I can without breaking it. I know this is no longer science. This is just me screwing around, but I need to know. Help.
Right. Yeah. Let's do
Okay,
this.
so I'm going to start at the bottom,
Yep.
which I know is good. Okay, and just inch our way up. Oh. Okay, and I'm good. Oh. Okay.
Dude, you actually jumped off it. That's even extra.
Sometimes I honestly sometimes forget about how strong our composites are.
Yeah.
I kind of want to redesign it even more spindly now. Like I feel like I could get away with.
You could get like an
way
extra
lower-
100 grams out or something.
I think I could get like an extra like 300 grams out. What's the 200 gram version?
I don't know off the top of my head. You
All
basically
right,
just
we're
have to-
not gonna find out. This is stupid. This looks good and it works. right, so I'm so stoked with how this project went, I don't even know where to start. Like, I've wanted 3D printing this good and strong for like the last decade, and it still like surprises me that it's our team that got the opportunity to like build and commercialize this technology over the last few years. And like now I get to play with it every day. The printer and the filament that makes these parts, you can actually just go buy off our website like today. And as of recent, we started offering OEM services where we'll work with you to like develop, qualify, and produce parts like this good to shockingly high volumes. Going into 2025, I'm like super excited. We have tons more stuff like this lined up. I get to spend a lot more time making content and like sharing crazy projects like this. Stay tuned for more, and it'll be totally worth your time.